Directorate seeks to answer a number of questions about the universe, including, are we alone in the universe, and how does life originate? How does the universe work? How and why is Earth's climate changing? The answers to these compelling questions are found in the wealth of data made openly available by NASA. Enabling discovery of these data and information is useful to both NASA and to the broader scientific community. We asked, could we leverage natural language processing techniques to provide scientists with an enhanced search and discovery experience that exposes useful connections to data? This project is unprecedented. Bringing together content from 5 unique scientific domains is a challenge. But success will help scientists to answer some of our biggest questions about the universe. Therefore, I'm excited to introduce the work of the SMD Knowledge Graph Discovery Team.
Hello, everyone. I am Megan Mark, and I am here today with Fexen, Marcella, and Rolene. And shout out to our great mentors, Gregory and Anna Maria. We are the Science Mission Directorate Knowledge Graph Discovery Team. Bucky Fuller saw knowledge as an expanding sphere, and the rate of this knowledge growth is called the doubling rate. This growth is a huge problem because the knowledge and the data is increasingly becoming more and more cross-domain or across different fields of science. And it can take scientists hours to find what they need, and it can be like finding a needle in a haystack. We can dramatically cut the time scientists spend looking for this data through the use of AI and knowledge graphs. So a knowledge graph is a tool for understanding how concepts are connected. For example, we have Apollo, and it is the node, and it is connected through an edge to John F. Kennedy. Well, John F. Kennedy is connected to the United States Agency for International Development, which is then connected to Servier. Servier provides satellite data to developing countries and works with Kenya. So Apollo is related to Kenya, and you wouldn't know that without the discovery power of a knowledge graph. We can use machine learning tools like natural language processing to tackle this challenge and to help accelerate new discoveries for NASA. For example, what if there was a cancer researcher who wanted to better understand how solar radiation affected astronauts for when we go back to the moon and Mars? Well, that cancer researcher might start with solar radiation, but as you can see here, there is a lot of data and they might not know where to even start. Wouldn't it be absolutely mind-blowing if this researcher could just go somewhere real fast, get the data they need, and answer those important questions? Our knowledge graph can help them do that. And we can build it by applying our pipeline to the text that describes all these data sets. To build the initial knowledge graph, we took all of these terms and information, and you can see that it is already getting really big. You can see there's 3 million terms in the Science Mission Directorate alone. So Marcella is going to tell you a little bit more about how this pipeline is built.
Thank you, Megan. So to play with all this data around us, first, we have to pre-process the information from several searches, vocabularies, data set, web pages, and papers from multiple domains. The pre-processing corresponding, for instance, to normalize the several types of documents we collected. In our pipeline, we address data from arXiv, Wikipedia, Science Mission Directorate vocabulary, and in UAT, Unified Astronomy Thesaurus, as Megan said. K-means is also applied to check overlapping across these multiple domains. From this data, our approach automatically extracted some terms and keywords from these domains using tools such as YAPE. We then connected the extracted words, creating a knowledge graph, which is a treasure map for us researchers. These words are connected using edges, and the linkage has been experimented with semantic similarity and co-occurrence. For the semantic similarities, we find the term bird on 2 separated datasets, one with only heliophysics and another hierarchically with both heliophysics and astrophysics texts. We then use their embeddings to compute the cosine similarity between the terms to study their relations. The knowledge graph is then human validated and also by quality metrics. And the visualization can be created with several tools, including Arena 3D, which is the one we selected for our case. Keep watching, and you will see Rolene presenting you amazing visualization of our graphs.
Thank you, Marcella. Before building the knowledge graph, we wanted to verify that there's an overlap between the different domains of the NASA SMD. We use k-means for this, which is a ML-based clustering algorithm, and we checked whether the clusters overlap. On this slide, you can see the k-means clusters for abstract of planetary science and heliophysics. K-means achieved the 80% classification accuracy. We achieved this high accuracy as the algorithm can distinguish between the two domains pretty well, but it didn't achieve the 100% accuracy as there are many overlapping terms. Now, I'd love to show you one of the knowledge graphs that we created. Here we go. This knowledge graph was created by extracting keywords from archive abstracts, and the edges are based on color currents. This graph looks a little bit like a bloom, and we will come back later to the term bloom. As you can see, it's like massive and super complex. This image alone just shows 1,000 edges, but the original knowledge graph has about 250,000 edges. Knowledge graphs can be very sophisticated, and we have been creating many different variations and have been looking at them from different perspectives. On this slide, you can see a multi-layer knowledge graph where each level corresponds to a level of the UAT. We are visualizing the top 5 keywords of all the archive extracts per level. We created links between the different layers if there are overlapping terms. In short, during FDL, we have considered many different variations of knowledge graph and experimented with different techniques. Now, Vexen will show you how our knowledge graph can help NASA and humanity.
Thank you, Rolene. This is what our Bloom Graph Knowledge Discovery search engine, which builds upon our knowledge graphs, could look like. Let's say that cancer researchers want to get solar radiation data. So go to the knowledge discovery and search for solar radiation. Behind the scenes, the search engine is looking at that knowledge graph to find connections to provide the best information. The search engine will then output the best data sets and potentially information that the scientists wouldn't have thought of. There is a connection between radiation and astronauts' health at the International Space Station. The scientists will not only be provided with the solar radiation data from the A satellite, but also the galactic cosmic rays data from the Voyager, as astronauts are exposed to both these radiations. And these are satellites beyond our moon. So not only does this benefit the cancer researchers, but all scientists and humankind. With this tool, we expect to at least reduce the search time by half through this high volume of information. We want to provide scientists this tool that will help them make discoveries and find solutions so that not only can we go back to the moon, but we can go to Mars and beyond. Thank you for your attention, and thank you to our partners for their incredible supports.
Wonderful, thank you. That's extraordinary. And I think it just brings to light a totally different dimension of the power of AI and machine learning tools to help us understand connections and to help us use natural language processing as a technique to sort of unravel very complex sources of information. So terrific. And we're going to jump right into the Why It Matters panel to kind of unwrap what we've just heard in these last two presentations. So joining us again is Massi Mascaro from Google Cloud. We also have Katie Baines from NASA. She's the Deputy Chief Science Data Officer. And from the US Department of Energy, we have Sunita Satyapal. And I believe we also have Marika Walchenko. So welcome, everybody, and love to hear your perspectives on what you've just heard. And again, since you're sort of up there in the upper left of my screen there, Massi, why don't you go ahead and weigh in?
Yes. Well, I mean, I'm super excited about these two challenges. Coming from Google, where our mission is to make information accessible and useful, I think this is exactly actually what we really kind of hope actually kind of will happen with technology. Let me make also an analogy and kind of a connection with the previous presentation. We always think about AI as kind of searching in this haystack of data. I think actually those two challenges really bring this even further. They now allow us to search into a haystack of knowledge. And this is super important for science, because science is not just kind of making inference, is understanding concept, is making connections. And these tools actually are really kind of a great step ahead in making that happen. I'll just also kind of mention that I love how the teams not only kind of applied really advanced research and NLP to find those systems, but they also kind of thought about how are we going to expose this to the end user? The end user doesn't need to be exposed to the complexity of what they're doing. And I think actually this is really essential. So I'm really blown away by both of those challenges, and congratulations a lot to the teams, and really looking forward to see how we can actually kind of make this really kind of accessible to a lot of scientists out there.
Excellent. Katie, from a science data perspective, what do you think? I think you might be muted, or
you haven't got your audio, Katie.
How about now? Good.
There we go.
Apologies. So it's really exciting to me because one of the things that we do within the Chief Science Data Office is look across all of the investments that NASA has been making in collecting scientific knowledge over the decades we've been around. But we've really historically had that fragmented into astrophysics research, earth science research, planetary research, and earth science. And it was never really intentional to tie all those things back together. So we end up with these fragmented data silos, these publications, this wealth of knowledge, and not a lot of effort been put forth to connect the dots among those. So, as we use AI/ML tools to sort of extract relevant sources of data and relevant connections, identify features, cluster the data in different ways than it's been clustered before, we're really able to amplify the useful findings and create new pathways to discovery. And I really like the example of how we can leverage radiation data, in a lot of different situations. And so finally, when I think about what this might unlock for us, and I really liked the H2 team looking at how they can match investments in the future. That's actually one of the things that if we uncover this sort of thing from NASA's data perspective, and we notice that data we're collecting for Earth science mission can be reapplied as we look to exoplanets, then we can look at how we adjust our investments in those technologies and those missions to see how we can continue to double dip or even really leverage the discovery in more than one realm. So really cool work and a really nice way to think about these things.
Yeah, that's amazing. And whether it's a data silo or a science domain silo, finding these tools and using these tools to break down the walls of those silos or look at the intersection where maybe there's more powerful insight, I think is so important. Sunita, what are your thoughts?
Great, thank you, Bill. And first of all, huge congratulations to the team. And it's been great working with you. And for us, it's really exciting. So really impressed by the creativity and just the capabilities of the team. So as you know, the Hydrogen Energy Earthshot was launched when the president asked our Secretary of Energy, how do we really accelerate progress towards the climate crisis? And I don't know where everyone's located with all the heat waves and the fires and so forth. I think we're all, really recognizing the urgency. So hydrogen is one key component. So similar to the moonshot, it's great to see, Katie, from over half a century ago, the idea of these energy earthshots are really to galvanize the global community. And hydrogen, again, is one of them, but there's huge potential to decarbonize with hydrogen. So as the team, and as Joe mentioned, we have to get to low cost. So that 1-1-1 goal, how do we get to $1 compared to, over $5, which is where we are today with electrolysis? So this approach of really rapidly being able to identify the promising pathways, how do we unlock opportunities, all of that I think is really, really critical. We have $9.5 billion now through the bipartisan infrastructure law. So again, this has been extremely valuable and look forward to following up.
Great. Thank you, Sunita. Well, Marika, I'm sorry, but we're running out of time according to the music, but if you have a quick insight you'd like to share, please go ahead.
Sure. I just want to say that I think what this team has done is great, and I'm really excited to see how we can take this and expand it within the hydrogen space to things like storage and delivery, and how maybe even people working in other areas could take the same approach and develop these kinds of tools in their own areas.